Hi guys, integration of y squared dA over the entire cross-section is equal to the second moment of area. Do you know why? Well, let's find out. Welcome back, and in this video I would like to discuss with you the process of developing a formula for the second moment of area of a cross-section using the method of integration. I, the second moment of area, is equal to integration of y squared dA over the entire cross-section. Okay, what is the second moment of area? The second moment of area, or moment of inertia, whatever you guys want to call it, is simply a measure of the section's ability to resist rotation or bending around a chosen axis. Why is the second moment of area so important? Well, we need to know the value of I for almost every criteria to carry out a beam design and to do a quick check on the strength of material. 1. To determine the flexural stresses in the beam, sigma is equal to minus my over I. Hey, we actually did a couple of videos explaining the derivation of the flexural formula. So I highly recommend you go back and watch these videos. I will paste the link in the comment sections below if you want to go and watch them. 2. To determine shear stresses, tau is equal to VQ over IT. 3. To determine the maximum deflection, say for a simply supported beam with a UDL, the maximum deflection delta would be 5WL to the power 4 over 384 EI. So the common relationship here between these equations is that I, the second moment of area, is the denominator. And that's how sensitive it is to all of these equations, so it's so important to get it right. Okay, most of us remember the formula for the second moment of area of a rectangular cross-section to be BD cubed over 12. But where in the world did that come from? How and why? Well, let us find out. Say we have a rectangular cross-section with a width b and a depth d. There are 4 main steps we need to look at during this process. The first step, you need to work out the centroid of the cross-section. In this case, because there is symmetry, then the centroid is right in the middle. The exact location would be at d over 2 and b over 2. The second step is select an axis of where you want this rotation to be about. You can really choose any axis you want and at any angle you want as well. And for every axis you choose, you will get a different value for I. For a simple rectangular beam with transverse loading, which causes the moment to rotate about the major axis, I would choose my axis of rotation to pass through the centroid, which coincides with the neutral axis. Why do you think this might be the best location to select the axis of rotation? Have a think about it. Well, because in a rectangular cross-section with a symmetrical bending, the area above the neutral axis is equal to the area below the neutral axis. So then rotating the section about the centroid would give us the worst case I for design purposes. So when we basically design, when we need to work out the applied flexural and shear stresses as well as deflection using all of these formulas we spoke about before, we can then compare these design values to the allowable limiting values and select an adequate beam size. Because I is located on a denominator of all of these equations, then it is very important to obtain the correct value of I, otherwise we may be under designing the beam. Okay, the third step is so important. We need to set up a coordinate system at the location of the chosen axis of rotation. Many times a lot of engineers forget this and values could be wrong. And so this is an important step. I have drawn up a 2D coordinate system to be located right at the centroid. I've chosen y up as positive, x to the right as positive. The axis of rotation is basically parallel to the x-axis. So at the centroid we will have a coordinate of x and y of 0 and 0. So that means x is equal to 0 and y is equal to 0 will start at the center of the beam. The fourth step would be using the traditional integration method to work out I, where I is equal to integration y squared dA. And we need to integrate over the entire cross-section based on the coordinate system we have previously chosen. So the first thing we need to do is take a little differential amount of area within the cross-section parallel to the axis of rotation and call it dA at a distance y above the neutral axis. So the first thing after we choose that, we'll know that the area of a rectangle is width times height. In this case, we can call the height a small distance dy and the width is b. Therefore, dA would just be b times dy. If you notice, we are integrating varying heights along the y-axis, and this is why we call this little height as a little dy, okay? In saying this though, the width is constant at b, at the value b, right through the height of the cross-section. If I had chosen my axis of rotation to be parallel to the y-axis, then I would be integrating varying width along the x-axis, and I would have written the area dA to be big D multiplied by little dB. So you get the idea here. Okay, then we can now plug dA in the main equation, and since I is equal to integration of y squared dA, therefore I is equal to integration of y squared b times dy, which is dA. We just plug that in. Now to set the limits to cover the entire cross-sectional area, where do you think the limits should be? Have a think about that one too. This is where the coordinate system that we have drawn up before becomes really important. Well, in this case, anything below the neutral axis is a negative value, and anything above the neutral axis is a positive value, while b is constant right throughout the height. So my limits would be from minus d over 2 all the way up to d over 2. Therefore, we can rewrite the equation integration of minus d over 2 to d over 2 y squared b dy. Then we can take the constant b, because it's a constant, we can take it out of the integration. And then we would basically have b integration of y squared dy and the limits. Then all it is after that is traditional integration. The antiderivatives of y squared would be y cubed over 3. So we can say I is equal to b y cubed over 3, and we have the limits. Then we can substitute the limits in the equation. So we get b with open brackets d over 2 cubed divided by 3 minus d over 2 cubed divided by 3, and then expanding it all out, we will get 2 lots of d cubed over 24. So d cubed over 24 plus d cubed over 24 is 2 d cubed over 24 divided by 2d cubed divided by 24. So that will be I is equal to bd cubed over 12. And this is when the axis of rotation passes through the neutral axis. And that is the centroid of the beam. Now, what do you think will happen to the value of I if we shift the axis of rotation and the coordinate system to be right at the bottom of the beam? Have a think about that. Well, everything is exactly the same. Everything is exactly the same as the previous example, except for one thing, and that is the limits of the integration. Because our coordinate system and the axis of rotation is at the bottom of the beam, so this means that the coordinates x and y, being 0 and 0, starts at the bottom and not at the center anymore. So this indicates that any value above the axis of rotation is positive. So the limits here across the whole section would be from 0 all the way up to D. This is just another way of saying that the entire area of the beam section is now resisting against rotation. So going back to the formula, I is equal to B integration y squared dy with limits of 0 to D. Again, the antiderivative of y squared is y cubed over 3. Then we'll get b y cubed over 3 with the limits 0 to d. And then after substitution from the limit 0 to d, we will get b d cubed over 3 minus d cubed minus 0 over 3. And b is outside the bracket. So that will end up being I is equal to bd cubed over 3. As we could see here, that bd cubed over 3 is 4 times greater than bd cubed over 12. So we can conclude that for a rectangular beam with transverse loading, the best location for the axis of rotation is through the neutral axis, which passes through the centroid of the beam. So yeah, this is where we derived the famous formula of bd cubed over 12, and we also learnt how to use the integration of y squared dA to work out the second moment of area. We hope you enjoyed this video and found it helpful. And hey, if it is morning on your side, then have a great morning, evening, have a great evening. Then over here, we always say, I hope you enjoyed watching this video and have a great afternoon.